Welcome students. In this video lecture we are going to talk about wave equation and the solutions of wave equation. So in the last class we have seen that the wave equation, it does admit a unique solution, right? You have a, you can actually talk about if you can talk about a solution. So let's say if there is a solution, then the solution is unique. That's what we have shown. Now in this part, what we are going to do is focus our attention on the existence part. Okay, but if you remember, for the Laplace and heat, yeah, if we wanted to talk about the existence of solution in the initial cases, what we were doing was we were looking for scaling kind of, yeah. In heat equation we looked at some scaling, if you remember, yeah. So basically functions which scale, and then with the help of that we deduce some fundamental solution, and in case of Laplacian also we have deduced some radial function, right? So we were looking for a radial function which are the solutions of the equation, and then since Laplacian is rotational invariant, and then we can talk about the fundamental solution. Here what we are going to do is nothing like that. So as I told you, see, heat and Laplace is they are like brothers kind of, yeah. Wave equation is a different thing, yeah. So in wave equation, the structure is very elegant actually, yeah. So for now what I am going to do is I am going to do it for n equals to 1. So the spatial dimension is 1. Okay, spatial dimension is 1, and after this we will do it for the higher dimensions. So in most of the books, or most of the general courses, the simple course which you do, the first course in PD, generally they treat the n equals to 1 case. Okay, so here we are going to do the n equals to 1 case, assuming that we do not know. I am quite sure most of you do not know even the n equals to 1 case. Okay, maybe you did not study it and in your course. So we are going to do that, and then we will go from there. Okay. So the problem which we have is, if you remember, it is a initial boundary value problem. Okay, so I am not writing all that initial boundary value problem. So the equation will look like this: utt minus Laplacian of u. Now n equals to 1, Laplacian of u is u xx equals to 0, right? This is in r cross 0 infinity. Clear? And u of course is g. Okay, so you will be given information on u where on the this thing boundary, yeah. So in this case the boundary is of course the base t equals to 0, and you will be given the value of u and ut. Ut is h, right? So this is on r cross t equals to 0. If you remember, in the bounded domain case, in the uniqueness case, what we did is u was g on the parabolic, on the omega t bar minus omega t, right? Yeah. So the closure minus the omega t, and here ut, the information of ut is given on the base. So here that of course that particular thing, because r is unbounded, this is essentially that boundary becomes r cross t equals to 0. Yes. Now here g and h are given. Okay, I am not specifying what they are. For now, let's just assume that there are some g and h given. I want to talk about it. Okay. Now, before I do that, I want to specify another thing. So this is just another reminder. See, the point is this. I don't know whether I have told you guys this thing or not. I should have explained it later before. So see, here in heat, Laplace, wave equation and all of this is required. All of this work has to be done. Why? Because you see, this problem, if I am just asking you to solve it, you guys can solve this problem. Of course you can do it, yeah. But the thing is, the boundary conditions has to be nice. G and h has to be nice functions. Otherwise the problem is, you see this problem. So for r cross 0 infinity, if this kind of domain is there, see, this problem can be solved by separation of variable, right? Separation of variable. And I think most of you guys know what separation of variable is. If you don't know, let me write it. It's basically this: u of xt is some function, let's say capital X of X, okay, and capital Y of Y. So you are basically capital Y of T, let's say. So basically you are looking for a function which is a function of X times function of Y. Now if you put it in the equation, that will split it up into two different parts. One is a function of X, so it will give you two different ODEs. Yeah, with this boundary condition, those ODEs can be solved. Maybe, yeah, maybe. There is no guarantee that it can be. Most of the times with nice enough boundary conditions, we can do it. Yeah. So after that, you do that thing and you get your solution. So on those things you guys already know. Yeah. Separation of variable. One very nice thing about separation of variable is it gives us an explicit solution. Okay. So one nice thing is it provides an explicit solution. Clear? Okay. So it provides an explicit solution, but this is a pro. But there is a con, and the con is a big one. The con is, see, it only holds for domain. So if you don't know, now you know. What I am trying to say is this: what is the main problem with separation of? See, generally what I see is most of the students, whenever I ask to solve some, let's say, heat equation, wave equation, Laplace equation, whatever, they start doing separation of variable. That is not true. You cannot use separation of, otherwise you see there is no point of starting any PD, right? You just do separation of variable, you get a solution and you are done, right? Okay, it is not true, because in most of the time the main problem is this: it does not hold for most domains. Yeah, let me put it this way: most domains. What I mean by most domains is this. See, of course, with this equation, with this relation, separation of variable you can use. But the thing is, for separation of variable to work, to get an explicit solution, you need these boundary conditions also, right? These boundary conditions. See, here the boundary is a straight line, or some nice boundary. So you can do this. But in a crazy looking domain like this, you can't use separation of variable, right? Okay. So it holds for most domains. It does not hold. Let me put it this way: it does not hold for most domains. That is, what I meant is, for rectangular domains, or triangular domains, rectangular domain, or disk, or the whole ball in Rn or something like that. Those kind of domains, it will work. It works, but not in an arbitrary domain. Yeah. So, but not in arbitrary domain. In arbitrary domain. So you do realize that this is a big con here. You cannot expect always your solutions to be in a nice domain like this. You cannot expect your solutions to be nice domain like this, or in the whole space. Yeah. So in those cases, what do you do? Then you are just left out with nothing, right? Okay. So these kind of things are used. These methods which I am going to develop now, they will be helpful in those kind of cases. Okay. Which is most of the time, most cases. Okay. Right. So let us come back to the method which I am trying to find here, and this is a very, very simple method. What I am going to do is this. See, this can be made more precise, but I don't think that we have the technical capacity of doing that. But I will just write down as much mathematically as possible. So what I am going to do is this. See, if you just write down this equation looks like this, no? Del 2u del t square minus del 2u del x square. Okay. So this is given to be 0. Okay, this is given to be 0. Now you see, you can write, this is an operator, of course. This is not a like a square minus b square kind of thing, but you can of course break it up, right? If you just do it. Yeah, I am not quite sure whether you guys know any algebra on operators or not, but you can write it like this. Yeah, del x del t minus, sorry, this, let me put it as a plus, there's no mistake here, but let me do it like this, u, this is equals to 0. I can write it like this, clear? So what I am going to do is essentially I am going to break. So this operator, see, this operator you can think of it like this, del 2 del t square minus del 2 del x square acting at u is 0. So that's an operator. Yeah, this is an operator. What is an operator? An operator takes a function and gives you back another function. Here it is taking a u and giving you back another 0. Clear? And giving you back a clear 0. 0 function, not a number 0. Function 0. Say everywhere it is 0. Okay. So this particular operator, what I am going to do is I am going to break it up into two parts. Yeah. This is mathematically true. You can of course do this thing, but the mathematics which is required for this, we did not do it right now. I don't think that most of you have seen this sort of mathematics, but for now you do realize that it should have been something like this, no? Yes. So this is coming from the algebra of operators. Okay, algebra of operators. Okay, so for now let's just assume this part. Yeah, I don't think that it is very difficult thing for you to assume, but because this is very straightforward, it's like a square minus b square is a plus b, a minus b kind of thing. Yeah, now this again I'm using some definitions of operator here. Okay, so please I mean bear with me here, because this will make life much easier. Now what you do is we set this thing, this particular thing, okay, as some function, let's say v. Okay, so set v of xt to be del del t minus del del x of u. Clear? So which is what? Which is del u del t minus del u del x. Okay, so see why I wrote it, I am always using the shorthand notation utt uxx. Here I am writing it like this just for you to understand that we can break it up like this. Yeah, otherwise you may get confused. So this is ut minus ux, right? So that's your shorthand notation. This is shorthand. Okay, so v looks like that here, and then so let's say that's your 2. Okay, let's call this as 1. So then from 2, what do you get? From 2, what we get is 1 second, let me see, from 2, what do you get? In terms of v, we get this vt plus v of x is 0, right? Because this is v, then this operator acts on v then. Yeah, okay, so that is 0, right? So let us understand what we are doing mathematically. Yeah, let's see that we are saying that I mean we are assuming that if you write an operator like this, so basically what we are going to do is, let's say a b times some function f. Yeah, if you have something like this, then I can write it as, I can just leave b out and I can look at a out, and I can look at how b behaves with on f. Okay, whatever it does, then I can take the action of a and I can work with that. Okay, so this is, think of this as a definition kind of. Yeah, so I can use that particular thing here. Now once I have this, that is giving going, it's an operator, so it acts on u and gives me some function v. That v, now again del del t plus del del x acting on v. So that is this. This is equals to the function 0. Okay, right. So I want to solve this problem.